So hello, welcome to today's seminar. Today's speaker is our Steve Butler, and he will be speaking about the RU project, Generalizations of Eulerian numbers.
Ah, how do you know it's my RU project? Okay, it's true. This is RU project, which some of you have met some of these people. A lot of you, of course, know Chris Cox, who was a former student here and is doing very well now at Carnegie Mellon in his PhD program. Esther, Banaian, Jeffrey Davis, Jacob Landgraf, and Scarlitte Ponce were all undergraduates who were here last summer, and I expect good things from those students, and you might see some of them in the next couple of months. I'm optimistic. I know several of them have applied here, and we might get one or two to actually accept. We'll see. So I want to talk about the generalizations of Eulerian numbers, so I suppose I should start by talking about Eulerian numbers. So these are defined in several different ways. So this is the Eulerian number nk. This is commonly denoted using these angled brackets. What does this count? Well, this counts something about permutation. So a little side note here. So I can think of a permutation in a few different ways. I can think of it as, how am I rearranging 1 through n? So there's two various notations that you often see. So there's the two-line notation where I write 1 up through n, in this case n equals 6, and down below I write the rearrangement in some fashion. And what does this mean? It says 1 maps to 3, 2 maps to 2, 3 maps to 1, so forth and so on. Sometimes you'll see this in just the bottom line because the top line is not very interesting. This is one-line notation, 3, 2, 1, 5, 6, 4. Now, once you have a permutation, you can start to count various things about it. These are what get into what's called permutation statistics. So there are two statistics I want to mention because they'll be related to Eulerian numbers. One is called descents, and what this is, in the one-line notation, it counts the number of times you have a large number than a smaller number in your one-line notation. So consecutive. So a large number followed by a small number. So for example, this is a descent because 3 down to 2. This is a descent, 2 down to 1. Now this is not a descent because 1 is smaller than 5, 5 is not smaller than 6, but this is a descent. So this has 3 descents. Now the other thing I want to talk about is drops. Now a drop, I talked about descents in one-line notation, just read from left to right, how many times you go down. A drop is in two-line notation, where what we have is we have a larger number and then a smaller number. So in other words, I'm decreasing my value when I map. So for instance here, 3 maps down to 1, so that's a drop. But 1 mapping to 3 is not a drop because it's not decreasing in value. On the other hand, let's see, do I have other else? I have 6 dropping down to 4. So this has 2 drops. So in particular, the number of descents, number of drops for this permutation are not the same. And these are not the same for almost all permutations. Okay, so now I can talk about sort of more or less the classical definition of Eulerian number. And what's that? Well, this is the number of permutations in the symmetric group of order n with exactly k descents. And this is the common way that it's defined. And then there's an exercise that says, well, show that this is also the same as the number of permutations in Sn with exactly k drops. And the way that this is often done in the second case is to do the following. It just says, well, show that there's a bijection between permutations in Sn to permutations in Sn, which takes descents to drops. And then you can show that these statistics are the same. Now, why do they have the name Eulerian number? You might think, did Euler really care about permutation statistics? And the answer, as far as I can tell, is no, he didn't care about permutation statistics. But he was a very smart guy, and he did a lot of things. And among other things he'd like to do is solve things using series and differential equations. So Euler has some motivation. Just, this is a little side note, where it gets its name, is if you try to solve the following, f prime of z is equal to t f of z squared plus 1 minus t f of z. If you solve that and you find the series solution, then what you get, if I done this right, you get that f of z is the sum of the Eulerian numbers e to the k z to the n over n factorial, something along those lines. And so that the Eulerian numbers showed up in solving that differential equation, which is why we call them the Eulerian numbers. This interpretation in terms of a permutation statistic is a more modern interpretation. Okay, so these are the numbers, and I can give you the first couple of these. You can do these by hand for small cases, or you can just trust me that these are the right numbers. So if I'm counting these, how many drops can I have? How many descents can I have? Well, if I look at any permutation here, there can be anywhere between 0 descents, which would say everything is going up 1, 2, 3, 4, 5, 6, all the way up to 5 in this case, or in general n minus 1. So let me write down the first couple rows. So we start off with 1. It's always easy to talk about the permutation statistic for the group with 1 permutation. Okay, after that I'll cheat and I'll actually look at my paper here. 1, 1, 1, 4, 1, 1, 11, 11, 1, and I'll write down one more, 1, 26, 66, 26, 1, and so forth and so on. Now, one of the things, of course, that you might notice and you might observe here is that you have symmetry, which is to say, if you look here, left to right, you get this nice symmetry going on. Now, that's actually not so hard to see. And the reason I say that's not so hard to see is if you go back to this interpretation in terms of counting descents, I can do the following. It says, you give me any permutation you want. What I'll do is I'll just flip the order, 4, 6, 5, 1, 2, 3. And what does that do? Well, it gives me another permutation. But more importantly, I say, well, where are the descents here? And I can look and I can say, well, where do I go down? The answer is I go down here, and I go down here. And those are the only two places I go down. And if you consider what's happening, it exactly corresponds where you have ascents in your original permutation. And since the number of ascents plus the number of descents is n minus 1, then it must be that if I flip it, I take whatever number here is, I get n minus 1 minus that number. And so that gives me a bijection, which gives me my symmetry. So it's very easy to see symmetry. All right, now, why do I care about this? What was our motivation? Well, Eulerian numbers show up in lots of different ways. And there's another way it shows up. Instead of thinking about permutations, I can start talking about rook placements. Now, most people care about rook placements. Well, for one thing, it's very fun. You can get lots of combinatorial out of rook placements. But nowadays they say, well, when I talk about rook placements, I talk about really these bizarre-looking boards with all these crazy shapes. So I'm going to do very simple rook placements, which says I'm going to take a board, some board, let's say, for instance, just to keep the example on for a little bit longer, I'll make it n by n, where n is 6. So here I have a 6 by 6 board. And what I'm going to do is I'm going to place rooks. Now, rooks are allowed to move, according to chess, along any row and any column that it's in. Now, if I just say place rooks, then it's very easy. I can put rooks wherever I want. But when I talk about rook placements, I talk about really non-attacking rooks. So I want to put one rook in each row and one rook in each column. So I guess there's another underlying assumption, which is I'm trying to place as many rooks as possible. So, for instance, what might I do? I might place one rook there, and a rook there, and a rook there. Then maybe I'll put a rook there. Let's see, is that where? Oh, whoop, no. I want to put one there, one there, one there. Okay. So there's where I'm going to place my rooks. Now, of course, this is not the only placement that I could do, but I want to make a connection here. If I look at this permutation here, I can correspond to every permutation this rook placement. Now how do I do that? Well, I look at how I look at the board, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. And what I do is if I'm looking at a permutation, if I have I pi of I, then I'm going to put a rook in the I pi I position. So this is the row, and this is the column. Now, because of my assumptions, I'm only going to have one rook in each row because I'm only going to have the numbers 1 through n here once, and I'm going to have one rook in each column because again I have numbers 1 through n here once. So this is a valid rook placement. And so in some sense, when you're studying the symmetric group Sn, you can argue that it's all about rook placements. Now how do I get back to these Eulerian numbers? Well, I can look at some of our interpretations. Now there's two interpretations I've mentioned. There's the descents interpretation, and then there's the drops interpretation. Now I want to think about what the drops interpretation means. So if I'm in a drop, what does that mean? It means that this pi of I is less than I. Well, pictorially what that means is that if I come to the board, pi of I less than I means that I'm in this part of the board. So I can now rephrase this Eulerian number. I can say nk, this is the number of ways to place n non-attacking rooks on an n by n board with k rooks below the main diagonal. So that's another interpretation of Eulerian numbers. And really, this is nothing more than just rephrasing what's going on with this interpretation over here. All right, well, so that's Eulerian numbers. We wanted to generalize it, but we wanted to talk about why are we going to generalize it? What do these numbers mean? So I'm going to take a detour here, which might initially not seem to have very much to do with Eulerian numbers, but we'll see in just a few minutes that, in fact, it's all about Eulerian numbers. So the REU project, our group was called the Math of Juggling, which means it was a very fun REU, and a lot of people want to participate. So for anybody who wants to run an REU in the future, just put Math of Juggling in your title, and you'll get a lot of people. And I don't know what it is, but apparently women especially like Math of Juggling. I had a lot of great women applying, and so that's another thing to keep in mind. Women like to juggle. Or at least they like the math of juggle. All right. Now, what do we have? Well, so what's going on with juggling? I'm going to just highlight a few basic ideas, but the math of juggling, there's the modern approach to this started about roughly 30 years ago, and it started with what's known as the site swaps. And the idea here is that we're going to describe patterns by throws. So in other words, I'm going to tell you the sequence of throws that I'm going to make. So by throws, in other words, if I have a ball here, I just think of that, there's a ticking metronome, tick, tick, tick. And so depending upon how many beats in the future I want it to land is how I throw it. So if I want it to land one beat in the future, I throw it really quick. Tick, 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 tick. So that's 1. If I want 2 beats in the future, I can do tick, 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 just a quick up and down. 3 would be something like this, and there's 4, and so forth and so on. So there's a sequence of numbers, and those numbers tell you how to throw the balls. So there's T1, T2, up through Tn. Now, one of the things that we implicitly assume is that these patterns are periodic, so in other words, they repeat. So we don't keep writing it over and over and over again. We say, okay, what's our basic building block? And then we can just repeat that over and over as needed. So, what's an example of this? This is math. But whenever I have math, I'm going to have to give a little bit of juggling to justify what this is. Does anybody have some favorite juggling patterns that they know they can come up and demonstrate? No. Okay, I'll just show you a few really quick, and I'll relate it back to the diagram in just a moment. So this is probably the most famous pattern that people know. This is pattern 3. Now, of course, just because we're talking about the math of juggling doesn't mean that we've taken juggling completely out of it. You know, because juggling is an art form, because you can do various things. This is also 3, but it looks very different than the other 3. And this is also 3, but again, it looks a little bit different. So there's still a little bit of mathematics, but there's a little bit of art. Now, this is actually different than 3. This is the pattern 441. This is the pattern that the mathematicians showed up at the juggling conference and said, hey, check this out. And the jugglers were like, ooh, those mathematicians, they know something. So, you know, it's a good pattern to know. This is called the baby juggling pattern, 52512. At one point it was going to be called Knudsen's baby juggling pattern, but he didn't want to be associated with that. So we don't call that. Knudsen's pattern is probably the hardest 2-ball pattern. I can't even do it, but let's see, I can embarrass myself. This is Knudsen's. This is 2-ball pattern. Yeah, I knew I'd embarrass myself. But anyways, so there's all these various numbers. Okay, so 333, 441, so forth and so on. Now, there's a question, and there's a lot of questions, but we start with some basic questions. You know, question number 1 is, well, when is a sequence of throws valid? In other words, I'm writing down this pattern of throws. When is it actually going to be something you can juggle? Because not everything can be juggled. Now, what do I mean by that? Well, suppose I think of time here, and I throw something that's like, let's say, 4, 3. Well, what happens? Well, this is going to land 4 beats in the future. So 1, 2, 3, 4 beats in the future. It's going to land there. This is going to land 3 beats in the future. That's going to land there. Now there's a collision because there's too many balls coming in at once. Because our basic juggler can only handle 1 ball at a time. We're going to relax that in just a few minutes. But for now, our basic juggler can only handle 1 ball at a time. So you have to avoid certain things from happening. Now this is one thing, but there are many possibilities that can occur. And it turns out that there's a very simple rule. And here's the rule. You need to have that T1 plus 1, T2 plus 2, so forth and so on, Tn plus n, mod n are all distinct. And that's necessary and it's sufficient. Now, what's happening here is that what you're really looking at is you're asking the question, what are your landing times? Modulo n. So you're asking, so which residue do your throws land in? So if I look at this, so for example, the balls thrown at T1, I think of those thrown at time 1 modulo n. When will they land? Well, 1 plus T1. Of course, again, there's modulo n, and so forth and so on. I just need to make sure that I don't have a conflict. So I don't want 2 residues to come together at the same time that causes collisions. All right. So what does this have to do with Eulerian numbers? Well, one thing I can do is I can look at a very special thing, because this modular condition says, look, I really don't care what happens mod n. So I can look at what I might call minimal juggling patterns. And that just adds an extra layer of conditions that just assumes that 0 is less than or equal to Ti less than or equal to n minus 1. Because it says, well, look, if I only care about mod n, if I add any multiple of n to a number or take off multiple of n, it doesn't change this modular condition. So I might as well assume that I've made my throws between 0 and n minus 1. So it's minimal in the sense of that throw. Now, there turns out to be a beautiful fact. So here's a beautiful fact. And now I'm not sure which one is this my eraser for? Well, I hope it is. Okay. So I'll call this an observation. Depending upon how serious you are, you can call it a lemma or a theorem. But it's the following. The number of minimal juggling patterns of period n using k balls is the Eulerian number nk. Now that might not be so obvious, but I'm going to argue in just a second that in fact once you have the right mindset, in fact, oh, it must be true. It has to be true. So what's the right mindset? Well, the right mindset is to think about what's really going on here. And it says the following. What you can think of going on here is you come to a board, and it doesn't really matter what your dimension is, and what I'm going to do is I'm going to think of my rows as the times that I'm throwing. What time do I throw? And then I'm going to think of my columns as the times that things land. So I have the throw times and the land times. Now when I talk about the throw times, I'm talking about modular constraints, because it's mod n. So for convenience, I'll do 1, 2, 3, 4, 5, and throw times 1, 2, 3, 4, 5. Now if we pause for a second and just sort of think about, okay, suppose we assume minimal juggling patterns, and I ask a question. Well, let's try to fill in, I'm going to fill in some entries here. Suppose I ask the following question. Suppose I want to throw it at time 2 and land at time 4. Well, how far do I have to throw it? So if I throw at time 2, land at time 4, what's my throw? And it's minimal, so it's between 0 and 4 here. This is not a trick question. Throw at 2, land at 4, I threw it 2. Okay, all right. All right, Bernard, good, all right. Next one, the student has to answer, okay. Okay, so suppose I throw it at time 3 and I want it to land at time 3. What do I do?
0.
0. In fact, it's not a very interesting throw, but that is a type of throw. And you can start filling things in. So these are not too hard to fill in up above the diagonal. Just sort of, what's your landing time, subtract your throw time. But suppose I'm a little bit more subtle. So suppose, for instance, I'm going to throw it at time 4, but I want it to land at time 2. What do I do?
-2.
-2. Fantastic answer. That's exactly the right thing. But our pattern for minimal throws says we always need between 0 and -1. So instead of saying -2, in this case n is 5, what does that become? It becomes 3. Okay, now I just have to remember where I was. That was right here. And so forth and so on. So I get this very nice pattern. Oops, except I need to make sure I put things in the right place. So in particular, given when I throw something and given when it's going to land, I can label things for myself. So I'm almost done. And here's the point. Every single minimal juggling pattern is a rook placement. Every single rook placement is a minimal juggling pattern. So what do I mean by that? Well, because I'm going to have to throw it at time 1, it's going to have to land somewhere. So wherever it lands, I don't know, suppose it lands there. Then that says that the first throw is a 2. And I just keep going. I can only have one ball at a time at any given location. And so I get that. So there's an example of a rook placement. So I get that the rook placement here, this rook placement corresponds with the juggling pattern 2, 3, 3, 0, 2. And if I were a little bit more brave, I say, oh, it looks like this pattern here. But I am not that brave. It's actually not such a bad pattern. It only needs 2 balls to juggle. But still, I'm going to avoid doing that. Kristen is checking. Does it really take 2 balls to juggle? It does, it does. Okay. Now, that tells me why there's a connection between minimal juggling patterns and rook placements. Why is there minimal juggling patterns and K balls? Gives me the Eulerian numbers. Well, the answer is, and this is another fun fact, is it turns out that the number of balls that you need exactly corresponds to how many rooks are below the main diagonal. This is not a very hard thing to prove. I'm not going to do it right now. So the number of balls is how many are below. So this pattern takes 2 balls. So that's how this follows out. So this is nice. So this tells me if I want to look at these minimal juggling patterns, I can really start looking at these rook placements and I can start counting various things. Okay, so this is stuff which is known, kind of. not as well known as I expected. I went and talked with, gosh, I'm trying to remember his name. Anyways, I'll remember at a very inconvenient time. But one of the people who was involved with CiteSop, and we were visiting him this summer, and we talked and said, well, you know, there's this nice interpretation. He was like, really? Yeah, it's in the paper you wrote. Oh, okay, all right. So he didn't quite have this down as much as I thought. So this is kind of a nice interpretation of how to think of juggling. And now, what was our generalization? Well, what we wanted to do is we wanted to do the following. Because what you can do, well, before I get to the generalization, why do I care about this? Well, the reason I care about this is because once you know your minimal juggling patterns, you can build them up. And so what do I mean by that? You can just add any multiple of n to one of your throws. So every juggling pattern corresponds to a unique minimal juggling pattern. You just pull off multiples of n until you get all your throws between 0 and n minus 1. But conversely, if you have your collection of minimal juggling patterns, you can build those up, and then you can get all juggling patterns. So in essence, you can count how many juggling patterns there are by first starting with your family of minimal juggling patterns and building up. And so this is why these are really useful and nice to know, and you can use Warpitsky's identity from this, which Warpitsky's identity is a nice identity involving Eulerian numbers, to count how many juggling patterns there are. It's not the easiest way to count them, but it works. There's much easier ways. That's a different talk. So we want to sort of say, well, let's think about a variation of juggling. So a variation of juggling, it comes back to this problem right here. So the problem that you have here is that you can't have conflicts where you have two balls come out at a time, because this is a juggler who's not very coordinated, also known as almost every juggler in the world, because it's really hard to work with more than two balls coming in at a time. But there are some jugglers who have mastered the art of what's known as multiplex juggling. So the idea of multiplex juggling is the following. You can catch and throw not just one ball at a time. You can do up to some parameter. I'll call it C balls. So C here, I'm thinking of C as capacity. So now you're a little bit more coordinated. You can now catch two balls at a time. You can throw two balls at a time, and so forth and so on. And we wanted to say, okay, suppose we let this generalization happen. We wanted to start understanding things. Well, from this perspective of minimal juggling patterns, the thing to understand is what's the right interpretation here. And so this is the answer. The right interpretation is to just change your rook placement rules. So now we are going to allow, I shouldn't say allow, we're going to require C rooks in each row and column. So now, previously, we just said, look, there's one rook in each row and column, and that's the rook placements. Now we're going to say, no, there's C rooks in each row and column, and now that's what we want to count. But the setup is basically the same, because really what's going on is we have the same board. We also have the same numbering. So the numbering doesn't change. So again, the numbers represents the various throws that can be made at any given time. The only difference now is we can make multiple throws at any given time, so we can now place rooks in various ways. So we can have rooks, for instance, like suppose I have C equals 2. Here's an example. I can have rooks there and there. I can put rooks there and there. I can even have two rooks going into the same cell if I want. That's perfectly allowed. And now it comes down to trying to figure out what's still allowed that I can get away with. Say there and there, and there and there. So this is now an example of the type of rook placement I want to look at. So in terms of juggling, what we do is we still list the throws, but now we put them together in blocks. So for example, initially there's going to be throws 0 and 3, and then the next round there will be throws of 0 and 1, then the round after that there will be throws of 2 and 2, and 3 and 0, and 1 and 3. Okay, By the way, in case you're wondering, there is an app for this. So you can go online and you can type in these patterns here, and it'll actually show you what the pattern is, and it can show you multiplex juggling. So this does work. By the same argument, which I didn't give, but so it must be true because I didn't give it. But by the same argument, what's true is the following. Namely, the number of balls is the number of rooks below the main diagonal. So this is really nice. In other words, I can just come in here and I can do this count. I can figure out the rook placements. I can say how many are below the main diagonal. And now I can start counting what I want. So here we go. Here's our generalization. So I'm going to write N, K, C. This is the number of rook placements with C rooks in each row and column, and K rooks below the main diagonal. So in essence, what's happening is that the Eulerian numbers correspond to C equals 1. Oops. So that's why we call this a okay. So the Eulerian numbers correspond to C equals 1, so this made a very nice generalization. Okay, well, obviously what do? The first thing you do is ask, has this ever been counted before? Now, if I ignore counting it with, say how many rooks are below the main diagonal, just say how many ways are there to place these rooks on the board with C rooks in each row and column. The answer is that has been counted. Okay, so I said, but what about this refinement? So we're doing a refinement of this count. Has that been counted? And what do? Well, you do what you always do. You generate data. And once you have data, you go into the OEIS and you type it in. You think of all the possible ways that someone might type this data in, and you check. And we checked. And the answer was no. No one's done this before. Of course, maybe it's because they didn't have a motivation, but we had a motivation. And this is not so unusual. Now, to give you some sense of the data, let me give you at least a little bit here. So, this was computed. This data was actually, I computed years and years ago. But I've been sort of stumped by it, and I'll show you the data here. So here's the data. So I'm going to do N, K, and 2. I'm just going to give you the first little bit. So 0, 1, 2, 3, 4, let's see if I still have enough energy to write all this down. So for n equals 1, okay, still 1, okay, good. For n equals 2, 1, 1, 1. N equals 3, 1, 4, 11, 4, 1. N equals 4, 1, 11, 72, 114, 72, 11, 1, and I'll do it one more row here. N equals 5, 1, 26, 367, 1492, 2438, 1492, 367, and then I can't fit it on, but the next numbers were 26 and 1. So this was some of the data. There's a lot more that we computed, but this is the data. So this, I had this data for years. I showed this data to Ron Graham because I've worked with him on juggling before. And he said, well, this is very, very interesting. And of course, anybody who looks at this data says, there's something really nice about these numbers, which is what? Symmetry. There appears to be symmetry here. 1, 4, 11, 4, 1. If I read it left to right or right to left, I'm getting the same numbers. And like everybody who saw this data said, oh, that's really, really nice. And so Ron showed this data to Don Knuth. And Don Knuth looked at it for 5 seconds and said, it's got to be symmetrical. Bet $100,000. He was convinced. The data convinced him. It's like, okay, well, that's great, but is it true? Well, it would be nice if it were true. The problem that we had was that our interpretation of the Eulerian numbers before had to deal with the fact that it would correspond to a permutation statistic, and then we can just get that nice symmetry by just saying, well, look, I can flip the order I write down the permutation. We don't have that nice interpretation here for a permutation, or somehow a family of permutation. So we've lost that. So we don't have that nice approach. But after thinking about it for a while, we came up with two different proofs, and in fact, this is symmetrical. So yes, symmetry is not a coincidence. So I'll give you an outline of one of the two proofs. In the interest of time, so what's the fact? This is equal to nc n minus 1 minus k c. So that's the symmetry that you see. And this, in fact, agrees with what you would expect when you have the original Eulerian numbers for c equals 1. Now, oftentimes the symmetry for the Eulerian numbers comes back to saying there's symmetry of the descents. This is going to be arguing that there's symmetry among drops. Because when I'm counting the Eulerian numbers in this board interpretation, I am counting drops. Now, the proof I'm not going to give you is the proof by juggling, which is really a shame because I really like the proof by juggling. It's a really fun proof, which is the proof by juggling says the following. This is a minimal juggling pattern. I can find another corresponding minimal juggling pattern, so I can get a bijection between minimal juggling patterns to other minimal juggling patterns where I go from k balls to c times n minus 1 minus k balls. And then that shows the symmetry. This proof is almost the same, but not quite. And here's the proof. So I'm going to give you a bijection. And it does the following. Take the board and shift cyclically one space to the right. So in other words, wherever your rooks are, move everything over one to the right. And by cyclically, I mean wherever your rooks are here, it just comes across to the other board. Now, what's happened here? Well, I'm interested into how many rooks are below the diagonal. So initially there were k rooks below the diagonal. Now I'm going to ask the question, well, what happens when I shift everything to the right? Well, when I shift everything to the right, I'm going to look at what's on or below the diagonal. So everything that was below the diagonal is still on or below the diagonal. Because I can move them up. I just went over by 1. So I have k rooks that were shifted over, plus everything in my last column is now over here. So after I shift, I now have c plus k rooks up here. On the other hand, I know how many rooks in total there are. I know there's a total of nc rooks, because I have n rows, each row has c rooks. So that tells me that up here, I must have nc minus c minus k rooks after I've done my shift. It's strictly above the diagonal. Okay, finally, so first you shift, second, you flip across the main diagonal. And now, the point here is that everything that's up in this part is now below the main diagonal. So that gives me nc minus c minus k rooks below the main diagonal. But this is a bijection because I can reverse this process. So now I've shown that the number of ways to put k rooks is the same as the number of ways to put c times n minus 1 minus k rooks. This seems like a very easy proof, and of course it is, after the fact. But it took a long time to think about, okay, how does this work? How does this work? Okay, so we have symmetry, and that was really nice. But we wanted to say, well, look, can we count anything? And the answer is mostly no. But we can get a few things. So what do I mean by we can get a few things? Well, for example, this turns out to be the Eulerian numbers. This is the same numbers that you'll encounter in the first column of the Eulerian numbers. This is actually not very hard to show. So there's another nice observation that you can make. And this observation is the following. I think I'm going a little bit slow. Okay, that's okay. So for k at least as large as c. So I have these three parameters. I have n, k, and c. If k is at least as large as c, if I look at the following, the Eulerian number n, k, c, then this is actually the same as the Eulerian number n, k, k. So in other words, if you're going to have, let's see if I get my employee, yeah. You don't think I got it right? So if k is fairly large compared to c, well then you might as well assume that c is equal to k. Somehow I feel like this is backwards, but let's see. Right, okay. Well, what's the proof for this? The proof is actually not so bad. We had a proof that took about a page. We used Hall's theorem. It was very fancy and very elaborate, where we found the perfect matching. Yes?
Like in that column you have actually k less than c, right? And it doesn't quite correspond, right?
Right, which tells me that in this column, I mean, you can always have k equal to c. You'll just, the numbers that you produce will be the same numbers. So that what's going to happen is you're going to produce nk1. So that's why I say this is the same as the Eulerian numbers, because you're just going to drop back down. So it's not a very interesting. That's why I say that this column gives you the same thing as the Eulerian numbers. I'm not saying that this is not well defined. I'm just saying that it turns out.
No. This is.
So, anyways, we got a very elaborate proof. Chris Cox came up with it. And then one of our undergraduate students, very good student. We want them to come, but anyways, that's a different story. Okay. He came up and said, look, this is really trivial by juggling. Because what's going on here? Well, what's going on here is it says the following. Let's see, I feel like my employees are wrong. But the point here is you look at how many balls you have versus how large your hand capacity is. And if if you have not very many balls, then that means that even if if you can throw and catch 10 balls at a time, but you only have 3 balls that you're working with, it doesn't matter that you can throw and catch 10 balls at a time. Because most of the time, the most you can ever really have in your hand is 3 at any given time. So that's why, look, if your capacity is too large, it doesn't help you at all. And so what that translates into in terms of the rook placement is it forces you to have lots of entries on the main diagonal. So lots of the rooks go on the main diagonal. And that's why you get this relationship popping out. All right, so let me state what the results we were able to get. We were able to basically knock out by hand this column, and I'll talk about what that is in just a moment. Using a computer, I believe we got the next couple of columns by a computer. Now when I said we got that, we were able to get a formula that tells you how to find that, or rather more precisely, we found a generating function. So here's what we have. Now, see if I can sketch the idea of the proof in the last 5 minutes. So, suppose I look at the following, the sum over all n of this parameter, n to x to the n. So in other words, I'm really just very narrowly focused. I'm looking at the generating function I would get in this column. So this would be, I can read off what it starts off as. There, it starts off as x squared plus 11x cubed plus 72x to the fourth, 367x to the fifth, and then the next few numbers, 1630, x to the sixth, 6680, x to the seventh, and so forth and so on. Well, it turns out that this is equal to x squared minus x cubed minus x to the fourth minus 3x to the fifth plus 5x to the sixth divided by 1 minus x cubed, 1 minus 2x squared, 1 minus 5x plus 5x squared. And that's what we have. So this really can nail down lots of things. You can really nail down, what's the growth rate. The growth rate turns out to be the root of this polynomial. It's a little bit messy. Now, the way we found this is we said, okay, let's think about all the ways we could actually do this. Now, this says there's not very many ways you can take this. So what I have here is I'm trying to place two rooks below the main diagonal. And how many ways can you do that? And the answer is, well, there's lots of ways, but more or less you only have 7 possible pictures. And so what are your possible pictures? Well, I can place them far apart from each other so that they really don't interact with each other. So that's one way I could place the two rooks. Another way I could do that is I could do the following. I could really put both rooks in the same cell. And then I get a picture like this, and so forth and so on. I can get them where they just barely interact. And there's nested. Variation of that, and I just want to show all of them, lest anybody accuse us of forgetting any. We did get them all, so here they're in the same column below the diagonal, and then you have the same row below the diagonal. So this was the 7 possible generic ways you could place the rooks. And we went through and in a very, very brutal, long process, we actually were able to figure out what happened on each one of those, and it took us about 2 weeks. But we got the answer, and we just kept going. We're like, we're gonna keep going, then we're gonna see if we're close at the end. And the amazing thing was we were actually right at the end. It was like, wow, it matched the day. We were so excited. But then we went back and we redid it, and it's now not so hard. And in fact, the whole process, we redid it, and then it only took us a few hours on a Saturday morning when we went through the second time. So it helps to do it a second time. So the basic idea, and I'm only going to sketch it because I know I only have about a minute left and I don't want to go over. The basic idea is, look, I'm going to place the rooks, and I'm just going to think about starting in the lower corner here. And when I start in the lower corner, well, suppose, it doesn't really matter which one I start with. Suppose I start here. So initially when I'm placing rooks, I really don't have any choice. I'm forced. So I'm going to move up one row at a time. And because I have to place two rooks, I have to place them in this column, and I have to place them in that row. I'm forced to go there. So there's really no choice. There's no choice. Now when I get to here, again, I don't really have a choice. I have to put a rook there. But here's the cool thing. That means that there's still a spot I can put another rook. And now I get a little bit of freedom. So now essentially I get two choices moving on up here between where I place the rooks. And so I get a little bit of freedom. And when I come up here, all of a sudden I get a lot more freedom. And so I take advantage of that. And what ends up happening is I can count, and this turns into generating functions to count things. I count the number of possible legal transitions. I throw in some parameters, and I get a nice generating function for how many ways there are to do a generic placement like this. Then I go do this and that for each of the 7, and I'm missing a ton of details. You can come talk to me. It's also posted on Archive, and you put it all together, and you get that. Now, this is a very tedious process. You wouldn't want to do it because the number of generic rook placements blows up really quickly. And so, but the computers, they love doing this stuff, you know. They love generic rook placements. So that's how we were able to get data for the next couple of columns, and also C equals 3, and I think possibly even C equals 4. There's a lot that we don't know. There's a lot of identities that you say, well, the Eulerian numbers have these nice identities. Do these generalized Eulerian numbers have such identities? Can you find a generic generating function? Because the Eulerian numbers have this very nice generic generating function. Is there such one for these generalized ones? I suspect not, because this is messy. When you see something like this showing up, yeah, there's probably something really weird going on, and it's going to be hard to count. And of course, going back to juggling, how do you go from your base patterns on up? It's a little bit more muddled than it is for just normal juggling when you throw in this multiplex variation. But anyways, that's other things. My time is up, so I'll stop here.
Let's send the speaker. Are there some questions?
Is there any particular reason you chose the ordinary generating function? Because in the example you showed before, it was the exponential generating function.
Well, it's a combination of ordinary and exponential. It just turned out for us that worked nicely. There's no really rhyme or reason why it has to be. I think mostly we did it because it mirrored what was in the OEIS. Because in the OEIS, if you look at the generating function given for the Eulerian numbers. So if you do this for 1, that sequence is in the OEIS, and then they give their generating function as an ordinary generating function. But I mean, there's no reason why we have to do ordinary, just other than it worked out really well when we didn't.
Earlier in the talk, you listed all of the Eulerian numbers and had it in that triangular layout. Pascal's triangle is generated by putting the binomial coefficients in a triangle in the same manner.
Right.
And an entry in Pascal's triangle is equal to the sum of the two above it.
Right.
Do you know if there's a pattern like that
Yes.
for the Eulerian triangle?
Yeah, so the pattern is, and I wrote this down because it's, so Eulerian number nk is n minus k, Eulerian number n minus 1, k minus 1, plus k plus 1, n minus 1k. This is not so hard to show if you go into the descent interpretation, because you can say, well, I want to make something with n variables which has k descents. So you can do one of two things. Either you start with something which has length n minus 1 with k minus 1 descents, and then you put something in to add a descent, and then it turns out you can do that in exactly n minus k ways. Or you start with something n minus 1 which has k descents, and you put something in so that there's no new descent added. And you can show that this can be done in k plus 1 ways. Now you can, and Chris Cox came up with a really beautiful proof in terms of the boards, which really is a nice way to do it in terms of drops. I haven't seen it before, but he's a very smart guy, so he came up with a nice way to do it recursively. So that's actually a great question. One of these questions is, here's this nice generalization, is there a nice recurrence like this? And I suspect the answer again is no. Because this really is very, very messy. And the reason I point to that is because you can really derive the rate of growth on a particular generating function by these coefficients. And because this is just going to have such a terrible rate of growth, I don't think you're going to have a really nice recurrence like this. But yes, there's a nice recurrence.
You can also pull that from the generating function, because once I have that, then I can create a differential equation that the generating function satisfies.
Yeah.
You could go backwards from Euler's definition and get that as well.
There's a class for that.
Yes, indeed.
But I don't know when that's being offered next year.
Probably next spring.
So let's thank Steve again.
And next week,